Summary of analyzing graphs of f prime and f double prime. Objectives: by this lesson, we should know how to interpret the graphs of f prime to find critical points, local extrema, increasing, decreasing, concavity, inflection points, and the second derivative where we can find inflection points and concavity. But before we start all that, let's talk about the normal graph. Right, so this is the general f of x graph. It's the boring one. Like, they're never going to ask you this question, but let's just use it to understand what everything is, right? So critical points, right, that's your local max and min. So that's what those are, local max and min. So when we say critical points, that's what we're talking about. So this guy here, that guy there, so those would be our critical points. Increasing, decreasing, right? Well, that's just literally where your graph's going up and down. So it's increasing from here to here. Then it's decreasing from -3-ish to 1, and then it's increasing from 1 to infinite. Concavity, I'll do that before inflection points, you'll see why in a second. Right, concavity is just, does it literally open up, or does it open, I guess that'd be down or up? Right, so like opening down would be something like this, opening up would be something like that. Inflection point is a point where like it goes from concave down to concave up or vice versa. So in this case, probably around like here-ish. But that's on a normal graph, like just understanding what everything is, what increasing means, decreasing means. Again, they're never going to give you this question on the test because it's too easy. What they will do is they'll give you one of the derivatives and ask you to do stuff like that. So in this case, given the graph of f prime. Now, I always say this, the key to doing all this is knowing your definition. You have to know your definitions. Very important. So I'm going to kind of break this into two different categories here. So given the graph of f prime, let's talk about the stuff that directly affects f prime. That is stuff like this and the stuff like this. Those affect the derivative. Right? It has to do with increasing, decreasing, critical points, and local minimax. The stuff that has to do with the second derivative are these guys. Concave up and concave down. And inflection points. So I'm going to treat them separately. First, let's talk about the stuff that's given the first derivative. That's just on your definitions. You have the first derivative. So if you want to find the critical points, just know your definition. The critical points where the derivative equals 0 undefined. So on your graph, you just look for 0 or undefined. If you want to find where f of x is increasing, decreasing, just know your definitions. It's where the derivative is positive or negative. Sorry about that. And then this right here, right? This is classifying your critical points. It's a local min or max. This is the first derivative test. And that's just a shorthand way of saying do a sign chart. Now you don't actually have to do a sign chart for everything. If we have the graph, you just read it. But the idea is behind the sign chart, right? Plus to minus, if it goes from increasing and decreasing, then it's a local min or relative, local max or relative max. If it goes from minus to plus, it's a local min or relative min. Right, that's what this is about. Now, what happens if they ask you about something that generally has to do with the second derivative, like concavity? That's a second derivative property, or inflection point, second derivative property. So here's my general hint with this. Here's my trick. If they ask you about the derivative, of your graph, think slope. That's the trick, right? So if I'm saying where's f(x) concave up, I would normally think, oh, that's where the second derivative is greater than 0. But I don't have a second derivative. We have the first derivative in this case. So I just change that to slope. This is where the slope of my first derivative is greater than 0. I'll do the same thing for this one, concave down. That's where the second derivative is less than 0. We don't have the second derivative, we have the first derivative. So this thing, where does the slope of the thing I have less than 0? Same thing works for inflection points, right? Inflection points, I just think that I know the definition. That's the second derivative equals 0 plus the sign change. We don't have the second derivative, we have the first derivative, so we just change this to the slope of f prime equals 0 plus the sign change. Slope change, we'll say. So that's my trick. Anytime they ask you about a property that's on the derivative below you, think slope. Just change the definition to slope and you'd be fine. Okay, let's do an example. So in this case, we have the first derivative. We have to answer some questions about the first derivative. So number 1, x values are critical points. So you just go, okay, What's that definition? That's where the derivative equals 0 or undefined. We have the graph of f prime. So where does it equal 0? Here, here, and here. It's undefined nowhere. So x equals -3, 0, and 4. That's all it is. If you know your definitions, it couldn't be simpler. Intervals increasing, decreasing. Again, know your definition. This is where the derivative is greater than 0. Increasing, I should specify it. And then decreasing where the derivative is less than 0. And if they ask you to justify, this is your justification. You don't have to overthink it. Why do you pick those values? Because this is what that means. Right? So if I want increasing, it's where my derivative is positive. Well, this is the derivative. It's positive here and here. So from -3 to 0 and from 4 to infinity. Or is it decreasing? Well, where the derivative is negative, we have the freaking derivative. So where's the negative? Down here and right here. -infinity to -3, union 0 to 4. So there we go. X values to the local min and max. So this is knowing, again, still the definition, right? How do you find local min and max? So the first derivative is a critical point. And then, local min is when you go from minus to plus. Well, critical points is right here. We classified them earlier. So we're looking from minus to plus. So this one goes from minus to plus. This goes from plus to minus to plus. So if we're looking for the local min, that would be right here, minus to plus, right? Because it looks like this. So -3 and -4. X values of the local maximum. Well, that's when it goes from plus to minus. So that would be at 0. And then usually the hardest ones for most people are the ones that ask for the second derivative. But again, let's use our trick. So find the intervals of concavity. So concavity is where, well, I guess we'll do concave up and then concave down. Concave up and I'll do concave down right here. Let me erase this. Erase a little too much. Concave up is where the second derivative is greater than 0. We don't have the second derivative. We have the first derivative graph. So I'm just going to change that to slope. So the slope of f prime I probably should write. So where's the slope positive? Well, when it's increasing. So right here, from -infinity to -2. That's where it's increasing. Probably should pick a color that wasn't the same as the line. And from here to here. Let me just highlight it, make it more easy. Like that, and like that. Right, so that's where my slope is positive, where it's also known as increasing. So concave up is from -infinity to -2-ish, union 3 to infinity. Well, let's say 3. And concave down would be the middle, where your slope is decreasing. Right? Because again, same concept. Concave down is where the second derivative is less than 0. We don't have the second derivative, so you just change that to slope. So where's the slope less than 0? That would be the middle. So -2 to 3. And the last one here, find the inflection points. So same idea. How do you find inflection points? So the second derivative is equal to 0 plus a sign change. Actually, or undefined. I don't have a second derivative, so I'm going to change that to slope plus slope change. So look at this one. Where does my slope equal 0 at? Well, here and here. And is there a slope change? Yeah, in this case, it goes from positive to negative, and it goes from negative to positive. So those are my inflection points. At x equals -2 and 3-ish. They're a little off. I'm going to say that's 3, I'm going to say that's -2. That's a little funky. But that's the idea. That's how you read the first graph. How about reading the second derivative graph? Now, there's actually a lot less we could get from a second derivative graph. And really all it could tell us is concave up and down and inflection points. And the second derivative test, I guess. But that's it. We can't tell increasing, decreasing. We can't tell critical points, really. So, at all, actually. So when you're given the second derivative graph, all you could tell is concavity and inflection points. Right? Concavity is when it's positive. The second derivative is positive, concave up. Second derivative is negative, concave down. Inflection points when the second derivative equals 0 and the sign, we have a sign change. That's how you get an inflection point. And don't forget the second derivative test. That's what this is. Right? All the second derivative test says is this. If you know it's a critical point, we can't find them, but they let us know, oh, it's a critical point. You plug that critical point into the second derivative. If you get a positive, that means it's concave up, so local min. If you get a negative, that means concave down, because second derivative is less than 0 is concave down. And you get a local max. Okay, let's do a quick example. This is the graph of f double prime. It wants to find the concavity, so concave up and concave down. Same idea. Know your definitions. Concave up is where the second derivative is greater than 0. So literally where the derivative is positive. If you have the second derivative. We have the second derivative, so where is it positive? From 1 to infinity. Concave down means where the second derivative is less than 0. Again, knowing your definition makes life so much easier. Right? So just go, okay, I know what that means. So where's the second derivative less than 0? Well, from here to here, so negative infinity to negative 2. I got to stop because at negative 2 it's 0, not less than 0. And then from negative 2 to 1. So we do got to break it up. So negative infinity to negative 2, because at negative 2 it actually does equal 0, so I can include that. And there we go. Find the x, y, z inflection point, so that's where the second derivative equals 0 plus the sign change. Now, second derivative equals 0 at 2 points, at negative 2 and at 1, right? That's where the second derivative equals 0. But only one of these has a sign change, right? This one here goes from negative to negative, and this one goes from negative to positive. So 1 is an inflection point, x equals 1, and negative 2 is not. That's usually a stationary inflection, horizontal inflection, whatever you want to call it. That's what usually that is. And then right here is the second derivative test question. Suppose negative 1 is a critical point of f, right? So negative 1 is a critical point of f. So that means it's a critical point, which means it could be a max or min. Determine if the graph of f has a local min or max. So all we're doing here is doing the second derivative test, which is plug that critical point into the second derivative and see what you get, right? If I get a positive, then it's concave up, so min. If I get a negative, it's concave down. So f of negative 1, well, here's negative 1. F double prime of negative 1, I should say, goes down here. Oops. So it's negative. This guy is a negative value, which means concave down. So x equals negative 1 would be a local max. Right, that's just implying the second derivative just a different way. If I know it's a critical point, all I gotta do is plug it into. All I gotta do is find the value at the second derivative and tell if it's a min or max. In this case, I knew negative 1 is a critical point. Let's plug it into the second derivative, which just means literally go to your graph and follow the graph. So at negative 1, my graph goes down here. So I have a negative value at negative 1. So local max, and that's the lesson.